Hey everybody, it's David with Isohorns, and today I want to talk about antenna patterns and antenna gain and beam width. I got a question from a customer about using an RF Elements Ultra Dish 27 dBi antenna as a point-to-multipoint sector, as shown below, which is a screenshot from UISP. So he's got his Ultra Dish here, and he's using that to provide service to these 10 stations. And he was asking if our 30-degree horn would be a better fit for this scenario. And I thought it would be an excellent opportunity to talk about antenna gain, beam width, and point-to-multipoint in general. So you can use a dish as a point-to-multipoint sector, but you need to have your stations clustered together like this here or like this here. But you can't have stations outside the beam width of the antenna. And dishes have more narrow beam widths than horns, and then of course sector panel antennas. And the beam width is basically a function of the gain. So as you increase the gain on an antenna, the beam width tends to narrow. And that's because gain is focusing the signal in a specific direction. So a larger antenna, when it comes to a dish, a larger antenna has a larger aperture, it has more gain, and it has a more narrow beam width. And so the 27 dBi, let's take a look at the RF Elements antenna pattern here. And I marked 15 degrees and negative 15 degrees from the center of the beam. And you can see that with a 30-degree coverage, the signal levels are going to drop off significantly. And a polar pattern like this represents the signal at the middle of the antenna is 0, which is this out here, this outer ring. So it's 0. And then this inner ring is negative 10 dB less signal than the center of the antenna, the center of the beam. So right here, you have 10 dB less than you would have at the center of the beam. That's at equal distances. So if you're 1 kilometer away at the center of the beam, then you're going to get this signal. And then if you move off, it looks like, about 10 degrees, then you're going to get this negative 10 dB less. And if you're off 15 degrees, then you're all the way, you're off the chart, basically. Your signal is going to be below negative 30 dB. You could get lucky and get one of these side lobes, but for the most part, you're looking at some pretty terrible signal if you're not in the main lobe. And so I'm going to take this, I'm going to copy it, and then I'm going to paste it onto this, and then shrink it down, and then rotate it. And we can see that a 30-degree antenna would provide reasonable coverage to these stations on the edge. If this is pointed here, these stations in this cluster can be serviced by this dish, but to service all of these with a dish, you'd need looks like you could reasonably hit maybe all of these stations with a dish sector, and then you might be able to break up these stations into 2 dish sectors. Let's take a look at what a 30-degree horn would look like. So this is the Isohorns 30-degree, and I'm going to take a screenshot of it. And so you can see here that with the 30-degree horn, this station on the edge would be at about, looks like negative 3 dB. And this station here on the edge would be about negative 6 dB. So the red is 4.9, and then the blue is 6.0. And so 5 gigahertz stations are going to fall somewhere in between the red and the blue. And this is how you read a polar pattern. So the polar pattern isn't a coverage. It's not like this is what you would expect the coverage to look like. The polar pattern is logarithmic. So negative 3 dB, which is this dashed line right here, is half the signal power of the bore side of the antenna. And negative 6 dB is called quarter power beam width. And that's 1/4 because it's on a logarithmic scale. But it's 1/4 of the equivalent signal as if you were at 0 degrees in the bore site of the antenna, the center of the beam. I hope this is helpful. Thanks for watching.